Okay, so let's start. So we are basically done with all the issues with registration, I think, including people from other departments. So, which basically means that we have a stable number of students that we can start talking also about projects, which I'm going to do in a second. Before that, I want to remind you that you're all working on homework 1, I hope. And homework 2, and it's due next week. About the same time, we're going to put out homework 2. Now, as will be clear, hopefully already clear from homework 1, will be even clearer with homework 2. So this class, as I said at the beginning, it's about applied machine learning. And the applied stuff is mostly going to be clear to you in the homework. So the idea of the homework is not that you just kind of spit out what we talk about in class, but rather you learn new things, you work on new things. So it's already, hopefully, something that you do. Okay. In homework set 1, but will be clearer as we go. So we will teach you new things during, while you are working on the homework, and we are going to expect that you think when you do the homework. So not everything is going to be completely clear. In some cases, in fact, we deliberately are going to try to challenge you and give you things that you really have to think about. That said, you have Piazza, you have a lot of TAs. Please use it and ask questions. Questions on the current homework. No questions. That means don't come after the class to ask me questions about the homework, because if you do have them, ask them now. Okay, projects. So as I said, it's time now to talk about it. So 519 students, which is about 2/3 of the class, students in the class have to do a project. The project is 25% of your grade, which means that it's supposed to be a significant project. I mean, not just something that you kind of do in a couple of afternoons. Which means I want you to start thinking about it now. I know that you don't know machine learning for the most part, but you will do the project in the second half or the third part of the semester. All you need to do now is to think about, what do I want to work on? So what I'd like you to do is to start forming teams. There are 116 students now registered to 519. We cannot read 116 project reports, so I'd like you to form teams of size 3 or 4. You will have to write a project proposal that will be due in about 4 weeks. So on the website, you will find details of what we expect in a project proposal, but basically, it's going to be a short proposal, 1 page, that will basically define what you want to do, why you want to do it, what do you know about what has been done on this, and it's mandatory that you have a few references. So part of the project is you have to read the literature. Don't give me URLs as references. It should look like a paper, both your proposal and your paper. So you'll use LaTeX, BibTeX, everything that is required to do these things. We have pointers there already, I think, for LaTeX style. So just make it look like a paper and reference other papers. So I basically want to make sure that you know what has been done on the problem you care about. So everything that has to do with machine learning is okay. So it could be an experimental project, it could be a theoretical project, could be a mix, could be even a critical survey of an area in machine learning. But again, given that it's 25% of your grade, it should be significant. So hopefully it will be interesting. Almost every semester we have really interesting projects, some really innovative. So hopefully you'll try to make it interesting. So I have a list here of a few things that, okay, so some examples. So before I get to this, so there's a lot of sources today for data if you want to do an experimental project. So Kaggle is one of them. There's a lot of projects that people have done. I'm giving here one example of an author paper identification. Given an author and a small set of papers, we're asked to identify which papers are really written by the author. You can think about author profiling, which is sort of a little bit a twist on this. Given a set of documents, profile the authors. Try to say something about the author. ID of the author, gender, native language. This becomes harder when you have papers that are written by multiple authors, but doable. And many, many other projects. So in this context, what I want to say is one important issue is there are data sets out there, but a project that is not acceptable is that you just go to a Kaggle data set and run a few algorithms on it. That's something that will take you an afternoon or two if you're organized, not the 25% of the class. So what I really want you to have is some kind of a thesis. So you want to say something about adaptation of the algorithm, the performance of the algorithm across different populations, and so on. Basically, have some hypotheses and try to use the data and what you know about machine learning as a way to prove it. Don't just run experiment and tell me, this algorithm gets 90%, this one gets 89, and so on. So that said, you can look at a few suggestions that I made here. One of them I already made earlier in the class. Develop a classification algorithm that can file my email into folders better than Apple does. It's a really difficult task. Conceptually, it's a very simple task, just multi-class classification, but they do about 50% or less. I'm sure you can do better. You can do, again, I'm giving here just a few bullets, and I'm going to read some of them. Name entity recognition is an important problem in natural language processing and information extraction. The idea is to identify phrases in text and type them semantically into this is a person, this is a location, this is an insurance company. You will actually play with data for name entity recognition in homework set number 2 in a very limited way, but it will give you some idea of what the problem is. One interesting thing is once you've trained a name entity recognition on 5 types, what happens if I now want you to work on another type? Can you figure out a way to adapt your learning algorithm or your model so that it behaves well on types that you have never seen before without damaging the performance it has on earlier types? Dealing with news stories. There's a lot of questions that you can ask about news stories. Some of these questions have become popular. Fake or not fake? That's relatively boring, but there's a lot of very interesting questions that you can ask. For example, you can look at claims made in news stories and try to identify contradictions between them, other relations between the claims. Do they say the same thing in different ways? Are they just a paraphrase of each other? Can you identify opinions versus facts? Many, many questions in this area. Spam calls. I know that you too get a lot of spams to your phone. This is something that has become very popular. Can you do something about it? And there are several things you can do about it. Some are machine learning heavy, some are machine learning not so heavy, but still very interesting. If you can prevent the spam getting into my phone. In general, there's a lot of data out there. I'm pointing here to another very interesting source of data, data.gov. Huge collections of data sets. Some are very, very large, that just by looking at it will give you ideas of what you can do. Last semester, one of the most interesting projects was about opioid, and people basically looked at statistics over many, many states and tried to predict the spread of the opioid epidemic across state borders. And again, the data is still available, really interesting. So basically, there's a lot of stuff you can do. So start thinking about it. Again, the one page is going to be due the weekend before, or before the weekend of the midterm. Look at the website. You'll also find when the midterm is. It's about 4 or 5 weeks from today, end of October. And just before it, a few days before it, is the due date for this proposal. Questions? Yes?
What are the paths the report should continue? It should look like a paper, but
it's on the webpage. So basically, a suggested table of content or way to organize the report is on the webpage. Yeah. Okay, good question. So in principle, no. As a student at Penn, you can get one GPU easily from Google. We're going to put on the website some instructions for how to do this. Beyond that, it's not so easy if you don't have other ways to get it. I'm hoping that this resource will be sufficient. We can think a little bit about whether we can provide more than that if your project really requires it. But that's an important question. So nowadays, where a lot of people want to do neural network-like projects, sometimes computation becomes an issue. It's not really easy to give you TPUs or many GPUs. Some can be done, yeah. Other questions? Okay, so start thinking, start getting organized. Okay, yeah, good question. So 419, you don't have to do a project. You can do a project. If you do a project, you will only gain from it, so it will not hurt your grade. If the grade that you get on the project is higher than the grade that you get on the rest of the class, it's going to help. One suggestion, 519 students, don't involve 419 students in your projects. And the reason is that I've seen it too often that 419 students don't have to do a project. So toward the end of the semester, where people are busy, too many classes, exams, and so on, they drop from the project, and you're on your own, or on two of you. I suggest to try to avoid that. But 419 students, if you want to form a group and do a project, you're more than welcome. Yeah.
How many hours do you expect us to work on this project? Do you have like some previous work that
Okay, so the first answer, many. I don't know how much time you spend on the class, but if you spend, say, 15 hours per homework, times 5, it's 75 hours. This is, I think 40% of your grade. So the project is 25% of your grade, something like that. So just do the math, if that's a good way to approximate it. But, you know, I'm not going to give you a number. But it's definitely not a few afternoons. It's more than that. Two, it's a good question. I don't think I'm allowed to make public earlier projects. Let me think about it and see if I can ask some students that did projects if they're willing to make their project available. Yeah.
What are you looking for in terms of like the teamwork and how individual people contribute?
Okay, so that's always a question you'll have to decide among yourself. So people come from different places here. People have different, expertise. You'll have to divide it in such a way that makes sure that everyone is involved heavily. I mean, I realize it's not going to be completely evenly split, but everyone has to be involved using their expertise. You know, just like any team effort, you'll have to decide. But definitely try to make sure that it's not, two of you are doing all the work and one or two others are adding their names to the paper. So. Okay, let's move on. I'm going to talk about it later in the semester, and please ask other questions if you have any, but we can move on. Okay, so where are we? So last time we talked about conjunctions. The reason we talk about conjunctions is not only because it's kind of an interesting concept class, it's also because it's very easy to deliver a lot of points that are important in general to learning using this relatively simple function or class of functions. So to remind you, we had this hidden conjunction at the top there, and we used 3 different protocols to learn it. We used an active learner, someone that asks queries, knows that there is a monotone conjunction that is hidden, and generates queries to a teacher in order to learn this efficiently. We use the teacher that basically teaches this concept and basically has to decide what are the good examples I'm going to give so that the student learns this concept quickly. And we also, in addition to devising algorithms for this, we also ask the question, so how many examples are needed in each one of these protocols? And we saw that actually the difference is quite significant, which means that the protocol actually makes a difference. The last protocol, number 3, was the one that is mostly studied in machine learning for good reasons. And in this case, some random source generates examples. We don't know how. There is some distribution that governs the generations of these examples. These examples are being labeled according to the hidden conjunction, and then a learner looks at a stream of these examples and attempts to learn what is the hidden concept. So we gave an algorithm. We call this an elimination algorithm. The way we described the algorithm was as an online algorithm. So you see an example, you hypothesize what could be the concept. Then you see the label and you see whether you're right or not. You update your hypothesis, you see another example, you make a prediction on it, you get a label, you update, and so on. And with this, we basically learned, and we got to a final hypothesis and observed, oh, by the way, it's not the only learning algorithm. At the end of last time, someone came to me, and I can't see you here, but if you're here, let me know, and suggested another very nice algorithm that is not an online algorithm. Basically uses the same principles, but a batch algorithm. Looks at all the examples, does something, and gets to the target hypothesis, which is interesting and fine. I'm going to think about it as an online algorithm because it's going to be easier for me for the next of what we want to do today and next time. But the bottom line is at the end, this set of examples allowed us to reach this final hypothesis. And what are the observations that we've made on this final hypothesis? Is it good? Is it bad? Is it satisfactory?
A little wrong.
It's a little wrong. So it's not exactly, unlike the previous two protocols when we learned exactly the hypothesis, here we didn't learn exactly the hypothesis. It's a little wrong. X1 was not eliminated. And we also discussed what does that mean, and we realized that we're going to make some mistakes. And that's basically where we end, right? So we talked about the performance of it and the kind of mistakes it's going to make. But I want to ask another example here, which is, how many examples do we need in order to learn this hypothesis, or in order to learn a good hypothesis? So you don't know the answer, and really the answer is difficult. We've seen, I don't know what, 15 examples or something like this, and we learned something, but it's hard to say something about how many examples you're going to see until you're good. We haven't defined even good in this case, unlike the previous two protocols. But I can modify my question, and instead of number of examples, I'm going to ask, how many mistakes are you going to make on this hypothesis, in this learning protocol, until you're happy or learn exactly the concept? So in order to make the question completely well defined, let's remind ourselves the protocol. So the protocol is, you have a hypothesis. I don't know, you start with something. I don't care how you start. In this case, you started with, say, all ones. All the variables are in the conjunction. You see an example. You use your hypothesis to make a prediction. If it's correct, you're happy. If it's incorrect, you change your hypothesis. You observe another example. You make a prediction on it. If it's correct, you're happy. If it's incorrect, you update your hypothesis, and so on. So rather than asking you how many examples you're going to see in the lifetime of the algorithm, I'm going to ask you, how many mistakes are you going to make in this learning protocol before you're happy? So let's go back to the algorithm, and this will help us. So we started with all ones. We predicted positive on it. What did that teach us? It just verified that this is a monotone conjunction, basically nothing. And then we saw a negative example, 1, 1, 1, all zeros, negative example. Did we learn something from it? Very little. But basically, we did not change our hypothesis in the algorithm that we proposed. And then we got to another example that was positive example, 1, 1, 1, 1, 1, many zeros, and then x98, 99, and 100 were also ones. Positive example. What did we learn here? So before, we thought that everything is in, right? So on this example, we actually made a mistake, right? Because when we try to predict on this example, we would say negative example, because not all the xi's are on. We made a mistake, but we learned something. What did we learn? After this example, the third example here, 5 ones, all zeros, 2 ones at the end. Yes? The ones in the middle don't matter. So how would you update your hypothesis? Now, you will basically eliminate everything between x6 and x98, and you'll just keep x1 up to x5 and x98, 99, and 100. One mistake so far. Here comes another example. 1, 0, 1, 1, many zeros, 1, negative example. Would you make a mistake on this? Okay, yes or no? Why yes? What would you think that this example is? So currently your hypothesis is x1, x2, x3, x4, x5, x99, x100. So on the fourth example here, you will say it's negative, right? No mistake. Next one. x1, x2, x3, x4, x5 are on. x99 is now 0. x100 is 1. Would you make a mistake on it? You will think that this is, you'll think that it's negative because x99 was in your hypothesis and x99 here is 0, but it's a positive example. So you made a mistake and you eliminated x99 due to that because you learn, oh, x99 isn't part of my target conjunction, and so on. Right? So that's the algorithm. So how many mistakes? So first of all, what examples are you going to make mistakes on? Okay, here are several things, suggestions.
We would probably make a mistake on positive examples.
Only on positive examples you'll make mistakes with this algorithm. And how many? Yes?
Isn't it hard to quantify the number of mistakes because each mistake can teach you a different amount?
Okay, but you can give me an upper bound. It's true, it's hard to do it exactly. You can give me an upper bound on, I'm not going to make more than these many mistakes. Yes?
100 mistakes.
100, why?
You said assume at each step we are eliminating one of the numbers, suppose x.
One of the xi's. Right, so it's true that here in the third example, I eliminated everything between x6 and x97 together because I didn't want to take us through 90-some examples to do it. But the worst case would have been that someone, an adversary, would present you positive examples where every positive example will teach you about one xi that isn't in the conjunction, right? And you will eliminate it from the conjunction because you've made mistake due to it, and they will do it one at a time. But once you've eliminated x50, you know that x50 isn't there. You'll never make a mistake that is due to x50. So no more than 100 mistakes. Yes?
I'm just thinking you probably get a pretty good expected value for how many examples you would need. So we know 1 in every 32, so 2 to the power 5 examples should be positive. If it's a random distribution of zeros and ones, because we have 5.
Okay, you're right. If I know what is the distribution, then I can compute expectation. But I'm going to assume here a worst case because I don't know what is the distribution. Keep this comment for about a week, and we'll start talking about thinking about distributions, and we'll see whether we can do something with this. But for now, I don't know what is the distribution. I know that there is a distribution, but why would I assume it's uniform? Right? In real life, distributions are not uniform, right? So I'm not going to try to guess a distribution or compute expectation. I'm going to be worst case here. And worst case is 100 because an adversary can present this example in such a way that every mistake I'm making, I'm learning one thing. And you're right, in general, I could be lucky and I can learn 90 things from one example. I'm going to count this as lucky. So basically, what have we said here? It's hard to quantify the number of examples. It's not so hard to quantify, or at least to bound, the number of mistakes I'm making. And this is really an important lesson. So we don't know how many examples, but we do know how many mistakes. And that's an important lesson because in many, many algorithms, it turns out that it's easier to bound the number of mistakes. In more general, in learning theory, people will call it the regret of the algorithm. So it could be a function of the number of mistakes, not necessarily the number of mistakes. But for us, it's going to be simple enough to develop a good intuition this way. OK, so we exhausted the learning conjunction, and we want to move out of it. But what I want to say is that there's a lot of lessons that we've learned from it. And this will guide us in two directions. One is, we talked at the end of last time about whether this new hypothesis that we learned, the x1 and x2, 3, 4, 5, 100, is good or bad. And you agreed that you're going to still make a mistake. You're going to make a mistake if a positive example comes along, but x1 in it is 0. Right? You will think that it's a negative example if x1 is 0, but it's not. Look at the true hypothesis. It could be a positive example. So you will make mistakes on these kind of examples. However, the probabilistic intuition is, well, you've already seen a lot of examples in your training process. None of these had this property. None of these was a positive example with x1 is 0 in it. So maybe these examples are very, very unlikely to occur. And also in test, it's very unlikely I'll see them. So don't worry. You're going to perform quite well on the test. So in terms of performance on future data, this is a good intuition. We're going to quantify this a little bit better as we go. This is, in fact, going to be the key intuition behind what is called the PAC framework, which is the key framework that people use to analyze learning algorithms. PAC stands for probably, approximately correct, and we're going to get to it next week. The second direction we can take is just, let's take the mistake-driven algorithm that we talked about now for conjunction and think about them in a more general way, develop a general algorithm, a general collection, if you want, of mistake-driven learning algorithms. Why do I call them mistake-driven? What we've done now is a mistake-driven algorithm, right? So we started with some guess hypothesis. We updated it as we made mistakes. If we didn't make a mistake, we just kept it. And we're going to talk a lot about these kind of algorithms. Okay, so let's move on and talk about these online algorithms. We're going to talk, the key algorithm we're going to talk about is the Perceptron algorithm with many, many variations. Then we'll also talk about the gradient descent view of these algorithms. And as we talk about these, we're going to talk both about the importance of representation, the complexity of learning, how difficult it is, how many examples you need, and so on, and introduce something that is called kernel-based methods, really some ideas about how to deal with features and expressivity of functions. Okay, so the first question I want to ask, in the case of conjunctions, you agreed with me that we bounded the number of mistakes. We don't know exactly how many, depending on the sequence of examples you'll see, but we agree that this algorithm that learns any conjunction over 100 variables is going to make no more than 100 mistakes. Is this a general thing? Is it clear that we can always bound the number of mistakes? Yeah.
If you have consistent data, if your data
if my data is consistent, which means I don't have the same example appearing in the sequence of examples with two different labels, which I'm going to assume is the case, you say yes.
I think so.
Why?
Because you can imagine that just through that iterative process, you can just always, as long as you have finite xi, you can always just, you'll eventually see an example that will show you the condition.
Okay, so you attributed it to the X, which is the instance space. What really matters if I want to talk about the number of mistakes? So here the instance space was of size 2 to the 100, right? All bit vectors over 100 variables. Is that the key thing in arguing that we can bound the number of mistakes or not? So I would like actually to think about something else here, which is the concept class. So what was the concept class that we talked about before? Yeah. The set of all conjunctions, all monotonic conjunctions. By monotonic, I mean no negations. So by the way, someone came to me at the end last time and asked me, I know about another notion of monotonic functions. Who was that? Who knows about another notion of monotonic functions? What's the notion of monotonic functions you know about? Strictly increasing. So a lot of you have seen in some other classes, calculus or real analysis or something like this, a definition of a monotonic function. What was the definition? It was if you move from x1 to x2, where x2 is greater than x1, the value of the function of x2 is also going to be larger than the value of function of x1. Right? An increasing function. This definition of monotonic that we used here, which says I have conjunctions but I don't have negations, is the same. Think a little bit about it. If you take two inputs, one input will be 1, 1, 1, 1, 0, 0, 0, 0 until the end, and another one is a larger input. What does it mean to be larger in the Boolean domain? It means that some of the zeros become ones. None of the ones become zeros. It's not going to be larger. Some of the zeros become 1. I claim that the value of the function, of a monotonic function, is only going to go up. If it was 0 before, it will not. It could go up. If it was 1 before, it will never go down. So it's the same notion, really. I don't know who asked the question. It was a good question. Anyhow, this was a detour. We are talking about asking ourselves, are we always going to be able to bound the number of mistakes? And in fact, the answer is going to be yes, but it's going to be an interesting yes, and it will have two parts. The first part is realizing that really it depends not on x, it depends, not directly at least, on the class of functions that we have. Now, in the case of conjunctions, how many conjunctions do we have over n variables? Okay, let's wait with this. You think about it. But it's a finite number, right? Finite number of functions. I'm going to denote this finite concept class by C here, capital C. Notice another side comment is that we typically distinguish between the class of target functions, C, and the class of hypotheses, which are the function our learning algorithm uses. Not necessarily the same. For the sake of this discussion, I'm going to make them the same. So the hypothesis classes that the algorithm uses and the set of target functions are going to be the same. So if I have a finite concept class, I argue it's completely clear that you will make a finite number of mistakes. Right? Why? Any suggestion? Yes?
You can't make infinite mistakes if there's not infinite examples, if there's not infinite possibilities.
right? And specifically, you can think about it this way. Let's enumerate here all the concept class, all the functions in the concept class, and make sure that my algorithm, when it makes a mistakes, eliminates at least one of them, because it uses a function here to make a prediction. It made a mistake, which means this function is no longer a good candidate. I made a mistake with it. Let's eliminate it from the candidates. So every mistake you're making, you look at the function that you used in order to make this mistake, and you say, oh, it's not this one. So basically, it's this algorithm. It's the consistency algorithm, the con algorithm. In the ith stage of the algorithm, let Ci be the set of all functions that are consistent with the previous examples. Okay? Choose one of them and use this to make the prediction on the coming example. If it's okay, it's okay. You didn't make a mistake. If it made a mistake, get rid of it. And now you have a subset of this set of functions that is strictly smaller. And so every mistake you've made, you've reduced the number of still remaining functions, and you will make at most number of functions in my concept class -1 mistakes. Okay? That's a complex way to say something very simple, which you said, which is I have these many functions. Every mistake using one of them is going to take it out. I have a finite number of mistakes. Yes?
So is the concept class here the class of functions your algorithm can learn?
So as I said, I'm unifying the target functions. I know that I'm working with the space of all disjunctions. So the hidden function is some kind of a disjunction over 250 variables. And my algorithm is also using these hypotheses. So to simplify our life, I'm basically unifying the set of all possible target functions and the set of all possible functions the algorithm can use. In real life, these may not be the same spaces. Is this clear? Confusing? Okay, so I actually argue that we can do better than this. So just, again, to develop some intuition. So really my goal here is for us to get used to the notion of hypothesis spaces, spaces of functions. So this was one exercise in doing it. The next one is going to be when you tell me that we can actually do better than size of C -1. Hint. What's the most important algorithm that you've learned in a computer science class or algorithm, data structure, whatever? The most fundamental computer science algorithm. Loop is not an algorithm. What? Greedy is a general approach. I'm looking for something more concrete. The most important algorithmic idea. Sort. You're getting close. What? Breadth search is an algorithm, but I'm looking for something even simpler than that. Binary search. Binary search, I think, is the deepest idea that you got from algorithms class. So let's use binary search here. And get a better, so you have a huge hypothesis space of functions. Some of them are good, maybe one of them is the target function. And I want to convince you that the number of mistakes that you're going to make is going to be much smaller than the size of this space. How do you use binary search? The idea of binary search here.
You need some kind of an algorithm between the functions which is not apparent here.
Yes, so computation is not an issue for us. We can be, I don't care about efficiency.
No, I'm talking in logical terms. So
Yeah.
to do that, you need to have some kind of an ordering between the functions. Like you need to have an order again in value because you need
True, true.
So that is not apparent here. I mean, how
But okay, so here is an example. Here are all the functions. Some functions say that this example is positive. Some functions say that this example is negative. That already gives you an order between them, right? Some are good and some are bad. How would you predict on this example? Again, some of these functions say this is a positive example. Some say this is negative. No one can abstain here, right? How do you predict?
Every time you make a mistake, you have the possibility.
Yeah, but you jumped a step. Before you do something, how do you predict?
you take a max, like
You do by majority. You ask, okay, so let's see how many think it's positive, how many think it's negative, and do by majority. If more than half think it's positive, say positive. If you made a mistake, what's going to happen now? Now is your answer. You eliminate at least half. That's your binary search idea here, right? So in principle, every mistake kills at least half of the functions because they misled you. If you made no mistake, you just stay this way. So this is the algorithm that I'm going to use. It's called the halving algorithm. In the I stage of the algorithm, I'm looking at all the functions that are possible here, right? Think about all the disjunctions over 250 variables. There's a huge number of them. You potentially look at all of them. All of them are consistent with everything I've seen before. So they're still here. And you ask them, how should I predict on this example? Some of them are going to say positive. Some of them are going to say negative. So given this example, ET, I'm going to consider, this is just writing what I just said, consider the value f of ET for all these functions and predict by majority, which means I'm going to ask how many of you say 0, how many of you say 1, and I'm going to predict 1 if and only if the number of functions that suggest to predict 1 is larger than those that suggest to predict 0. Clearly, if I made a mistake, I can eliminate half of them. So Ci plus 1, which is the number of functions that remain in the I plus 1 stage, is less than a half of what I had before. And therefore, I'm going to make log C mistakes, which is much, 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 much smaller than C mistakes. Okay? Yes?
Well, in this algorithm cause overfitting, because you're like testing on each point in that. So,
Okay, so first, I don't necessarily test on each point. What I do is I touch each hypothesis, not each point. The number of points I'm going to touch, I don't know how many there are. I don't know how many points. So you give me a point, I'm in principle touching all the candidate functions and ask, what do you think about this point? Okay? I may touch only 50 points because after 50 points, I'm going to eliminate all functions but one. Okay, like in the example that we had before with the conjunctions, I could have touched 100 examples, even though the number of examples in my space is 2 to the 100. Okay? That's one point. The second, this is not a practical algorithm. This algorithm forces me to touch all the functions. There's a huge number of functions. But it tells me that in principle, if you have these many functions in your space, you don't need to make more than log of these mistakes. Of course, one of the questions we're going to ask now is, so I call this a theoretical algorithm here, right? It's not really a practical algorithm. But I'm going to ask, is it practical? Or how can we make this practical? So let's go back to the space of conjunctions that we talked about before. Yes?
So I think his point was that you're not allowing your hypothesis to make any mistake on the given data.
True.
So even if you try to make this a practical algorithm, it will kind of overfit, right?
Not clear. It's so far when we talked about learning, we always insisted on doing well on the training. So I want to do perfectly on the training. It does not mean that I'm going to overfit. We're going to talk about how to go from the performance on the training data to the performance on test a little bit later. But it's not completely clear that I will overfit if I'm learning with something that is quite simple. You know, go back to your badges example, right? So you did not make any mistake on the training data. Nevertheless, it generalized quite well because it was a very simple class of functions. So I understand the intuition. So that's an important intuition, but it's a slightly different game that we're playing now. Does it answer your question? Okay, so what have we done? This is just a brief summary. We talked about, bottom line, a theoretical algorithm for bounding the number of mistakes, and I want to take the concrete example of conjunctions. Right? So we have a hidden conjunction. This was the hidden conjunction. Okay, so that's actually, how many conjunctions do we have? Let's say I put the answer here, so let's just see if we can convince ourselves that this is true. The number of conjunctions over n variables is 3 to the n. Why? Anyone wants to explain?
Each literal is either not present in the conjunction, or is it positive, or is it negative?
Right. So 3 options for x1. It could be not there. It could be x1, and it could be not x1. And I have n decisions like this, so it's 3 to the n. Huge number. Now, log c is about n, whatever log base you care about. So much, much smaller. Now, if you think about the elimination algorithm we talked about at the beginning today, it basically does n mistakes. Right? So makes sense. On the other hand, the elimination algorithm is going to make n mistakes whenever the class is conjunctions. If I'm telling you now, really, the target function is going to be k conjunction, which means it's a conjunction over n variables, but only k are going to be there. Okay, I wrote disjunction here, but it should be conjunction. The same game is going to work for disjunctions. So you have 100 variables in your vocabulary, but only 10 of them are going to appear in the conjunction, which is a more realistic type of functions. Function space that we really care about are sparse. That's why we can do learning. How many k conjunctions are there? 100 choose k. Why?
You need 12k places with the 100, but
Right. So it's a little bit more than that, because you first choose the variables. So you choose the k, but then for each, and you chose the 10 that you want to include in the conjunction. Now you have to decide, are they going to be negative or positive there? So it's 2 to the k times this. but it's not a lot more because k is a fixed number, a small number. So it's a lot more though. It's a lot less than 3 to the n. What is the log of this number? N to the k behaves, n choose k is kind of like n to the k. If you haven't seen this before, convince yourself by writing what is n choose k. So the log of it is basically k log n. So let's compare between n and k log n. K log n is much, much smaller. Is it possible to learn efficiently with this many mistakes? So the elimination algorithm is not going to do it. The elimination algorithm doesn't care about this k. It's always going to make order of n mistakes. Are there better algorithms that can learn efficiently with only logarithmic number of mistakes in the dimensionality, which is going to be very cool. Okay, so basically, can this bound be achieved? We're not going to talk about it in class, but in the homework, you're going to see an algorithm that actually can achieve this. So that's one, we answered half the question that I wanted to ask. Can we bound the number of mistakes? We gave a theoretical algorithm that says yes. Can we bound it also in practice? And we gave kind of two bounds, one pretty loose, another one that is pretty tight, but we didn't give the algorithm that achieves it. But it's possible to achieve. Now, the second thing that we want to ask is, okay, but in this case, we basically worked with finite hypothesis spaces. Conjunctions, disjunction, Boolean functions. The number of functions over n variable is large, but finite. What happens when we move to the real domain? Can we also bound it there? I don't know if you guys have any intuition here. The answer is going to be yes, which is kind of surprising, right? Because now you have infinite number of functions, and still we're going to show that even though there's infinite number of functions, you can still bound the number of mistakes a learning algorithm make. Okay, so let's make a few steps toward this, and I'm just reminding you of some notation that you've already seen so that we get there today. So the class of functions we're going to talk about are linear functions. We call them linear threshold function or linear threshold units. These are this dot product W transpose dot product X minus theta. And I reminded you last time, or a few times already, that the conjunctions that we talked about, the disjunction that we mentioned, haven't talked about, and if many Boolean functions are really linear functions. And you've done this conversion also in the quizzes, so I'm not going to dwell on it. We also talked about the fact that if a function isn't linear, it can be made linear by changing the dimensions. So just as a point of connection between what we've done with conjunctions and the linear function representation of it, you can think about the elimination algorithm. Instead of keeping a hypothesis of conjunctions, before we talked about, the elimination algorithm starts with thinking that all the variables are in the conjunction, x1, nx2, nx3, up to x100. And then as we went on, we eliminated some of them from the conjunction until we got to x1, and x2, and x3, and x4, and x5, and x100. You can also think about it as a weight vector. And the weight in the weight vector indicates whether you think that the variable is in the conjunction or not. So you start with a weight vector that is all 1, with a theta of n, and the algorithm changes when it decides that x98 is not in the conjunction. It changes the w98 from 1 to 0. It's completely equivalent. So at the end, it will learn this linear function, w1 x1 plus w2 x2 plus Okay, I didn't include the 100, up to x5 here, minus theta. So it's basically just changing a vocabulary. It's really the same thing that we've done before. So if you really wanted to make sure that you understand the mapping from this Boolean function to the more general class of function of linear threshold unit, here it is. Questions? Okay, because I know that some of you had some questions on this, on understanding why these Boolean functions are the same as linear threshold functions. It's clear. Okay. So again, I want to take a small detour and say there are many reasons we want to learn linear functions. They're more expressive than just Boolean functions. They're more flexible, right? So you can, it's infinite class of functions. You can say a lot more things. But even if you cared about conjunctions only, which is also an interesting class of functions, even then, I would recommend use linear functions rather than conjunctions. Why? Well, it's not as interpretable, but it has complexity advantages. So if you really want to learn conjunctions, should your hypothesis space be the class of conjunctions? So there is a theory that would say no. Because if you really insist on learning the conjunction, the best conjunction consistent with the data, it's actually an NP-hard problem. So don't do it. Instead, and I'm not going to give the reduction. People that know about NP-hardness will understand this better. People that don't, just record the fact that it's a hard problem. On the other hand, if you want to learn, you can learn this conjunction as a linear function, and this problem becomes easier. Why is it becoming easier? The intuition is that the space of linear functions is much, much larger than the space of conjunctions over a given number of variables. And the same conjunction is represented there many ways, many times. The same conjunction is going to be a point in this huge space of linear functions. So your algorithm will just find one of these representations, not necessarily the best one or the shortest one of these. So the combinatorial problem of searching the space becomes much easier because the space is larger. Yes?
What's the time scale?
So that there is a polynomial time algorithm for that. It's essentially linear programming. Not necessarily we want to use this algorithm, but there exists a polynomial time algorithm for that. Okay, so that's, if you needed another justification, we want to learn linear functions. Yes?
I thought that this is a simpler problem because the space is smooth. And you increase one variable a bit.
That's a good intuition, but it's not a computational intuition, right? So, because it doesn't tell you how many steps you'll have to make in this continuous space. So it's true that sometimes we want to work in a continuous space because of this, right? Because things are smooth, there is a notion of distance that is continuous and so on. But it's not necessarily the case that this translates to computational complexity. So in fact, the computational complexity of the algorithm that exploits this smoothness is larger than the discrete algorithms for the same problem that do not like linear programming, that do not necessarily exploit the smoothness. So this intuition is, I don't know, it's good, but it's not always enough. Okay, but I just use this as a way to convince you, let's talk about learning linear functions. So what does it mean to learn linear functions? It means that we are embedding all our data in this vector space, high-dimensional vector space, to here, and we have a hypothesis, W. And we're going to move this hypothesis W in the space until we're happy with how well it separates our data. So what I'm showing you here is the vector W, which is going to be our linear separator. And this vector W is perpendicular to the hyperplane that defines the set of all point X that satisfy W dot product X is 0, right? So this is something that you should be happy with. We can also add the theta here, and we're moving this line away from the origin. So now we have the blue line is the set of all points X such that Wx is equal to theta. Above it, greater than theta, below it, less than theta. And that's what we are after. Okay, so one additional comment that we already said before is this move to the canonical representation by adding one dimension, so I don't need to carry the theta with me all the time. Again, you've seen this before, hopefully it's clear, and I don't need to carry theta with me, and let's move to an algorithm. So the Perceptron learning algorithm has a very interesting history, and I'm going to actually tell this history very briefly. First of all, it's an online algorithm. By online, I mean I see example one at a time, I predict on it, and then I change or do not change my hypothesis. It's mistake-driven because I'm going to change my hypothesis only if I make a mistake. If once I predicted on the incoming examples, I was happy with my prediction, I'm not going to change my hypothesis. Okay, so it's an old algorithm, was invented in the 50s in the US and in Russia at about the same time, or the USSR. Rosenblatt, in 59, developed this algorithm, wrote, basically he was a neuroscientist, he thought about it from this perspective, and he said, and these are basically his words, that when a target output value is provided for a single neuron with fixed input, it can incrementally change weights and learn to produce output using this perceptron learning algorithm. So this is what he had in mind. He had in mind X's in the input, weights on the wires from the input to this summing unit, and then a threshold function that decides whether it's on or off if the sum, the weighted sum, exceeds the threshold or not. Mathematically, we learn a function that is going to map from X to plus or minus 1, represented as the sign of W dot product X. X could be either Boolean, 0, 1 to the n, could be real valued. W is always going to be real valued. And specifically, the algorithm is going to be given labeled examples, in this case, M labeled examples, X, comma, Y. My notation is always that bold faces are vectors. So X1 is a vector, Y1 is a label, plus or minus 1. X2 is a vector, Y2, I hope that, yeah, it's pretty clear that these are bold. Here's the algorithm. So I'm initializing W as a real valued vector. I'm cycling through all examples, in practice, multiple times over these examples. I'm going to predict the label of instance X to be Y prime equal the sign of dot product WX. Now, if Y prime is different than Y is the true label, Y prime is my prediction. If Y prime is different than Y, which means I made a mistake, I'm going to update the weight vector. Otherwise, I'm going to leave the weight vector unchanged. How do I update when I made a mistake? I'm taking my W, and I'm replacing it by W plus RYX. What does that mean? R, think about it as a constant, learning rate, step size. Let's think about it as 1 for now, so it will not confuse us. What does it mean that I'm adding to W, Y, X? X is my example. y can be plus or minus 1. So if y is plus 1, which means the example is positive, I thought it's negative, right? I made a mistake. So I'm adding the example to w. If y is negative, which means the example is negative, I thought it was positive, because I get to this stage only if I made a mistake, I'm subtracting the example. So essentially, I'm starting with w, and I'm either adding x to it or subtracting x from it, depending on what mistakes I've made. That's it. Very simple algorithm. So let's just look graphically and try to understand what's the behavior of this algorithm. Oh, wow. Okay. So, in fact, we're going to start with this next time. I realized that I ran out of time. I want to say one more thing. So think about this algorithm. Think also about the case where it so happened that x is Boolean. Let's assume that the x's are just 0 and 1s rather than real values. What does that mean about the behavior of the algorithm or how you write the algorithm? It becomes a little bit simpler, and sometimes it's important. And this is basically where we're going to pick up next time. Questions on the algorithm? Yeah.
So that means if x is 0, 1, it means that if x is 0, then it's never ever going to flip to 1, right? Because you're only ever...
Okay, good. So basically, if I have a vector x, which is 0s and 1s, it's true. If x7 is 0, it means that... Well,
you're only ever pushing them down to 0, not making 0.
So in terms of the update, so when I add to w yx, I have to touch all the dimensions, right? In every coordinate, I have to add the x. But if x is only 0 and 1s, what does it mean that I have to do? Only those that are 1 I have to touch, which means that if I have a million features, but only 100 of them are on, I'm not going to represent all the million features, in fact. I'm just going to get a list of all those that are on, and the algorithm is going to be a lot more efficient now. I'm going to touch only the active variables. So that's very important implementation-wise. Okay, other questions on the algorithm? Okay, so we'll pick this up on Wednesday. See you. Hi.
In the linear programming algorithms, they do leverage the fact that it's smooth, right? I mean, simplex moves along the edges.
Yes, but not those that have proofs for. Simplex, we don't have a proof that it's polynomial. So there is some interesting thing here. So those that we can prove something for are discrete. And those that work better may not be discrete. But we don't have tools to prove something on them.
Isn't that NPR?
It's NPR. No, linear programming? No, it's polynomial.
So what do you mean by discrete? I mean,
So discrete like learning disjunctions, for example, right? So for these, we know that it's hard.
Wouldn't that be integer linear programming?
No, it's you can formulate learning linear separators as a linear program. So in fact, I can show you. I mean, I used to have a problem set on this, but it's a hard problem set. But it's actually a nice reduction. You can write even with margins. You can do it with margins as a linear program.
Also, will we discuss the infinite concept class having a bound on the number of mistakes in class?
Yeah. This is Perceptron. I mean, we're going to get there in 15 minutes. Yeah.
I just had a doubt in halving algorithm.
Yes.
In halving algorithm, do you have the labels already before prediction?
I don't need to have the labels, no. So I have an example, and I'm asking for the predictions of all the concept class. Only after they give me the suggestions, I'm predicting, and then I'm testing what is the. Then someone gives me the label, and I decide whether I was correct or not.
Okay, so in that case, that one iteration would be enough, right?
What do you mean iteration?
One iteration, one repetition would be enough, right? Because whatever are false, whatever conjunctions that are false, that would go out, and the remaining would be true. And then why are you running it again and again then?
No, I'm not running it again and again. It's
You're
just
only running it once?
I'm running it. Well, I haven't. Think about it this way. I have a stream of examples that come.
Okay.
I'm going to run it until I eliminate all the inconsistent hypotheses. So I'm going to run it log size of C times. So in fact, I don't talk here about the number of examples. I'm just talking about the number of mistakes. How many examples will I need to see in order to make this number of mistakes is not known. You see, there's a difference between the number of examples and the number of mistakes. I don't know how many examples I will see. Maybe my first million examples I will make no mistakes on.
In that case, you'll keep all the conjunctions or all set of conjunctions?
No, so I have my hypothesis, let's say,
Okay.
right?
Yeah.
Again, remember it's a theoretical algorithm. No one is going to use this algorithm. But the idea here is that when I analyze it based on the number of mistakes, I don't know when I will make these mistakes, right? So it could be that I'm making, in a practical algorithm, I have some hypothesis, I make no mistake, no mistake, no mistake, no mistake, no mistake. I just don't update it. I keep my hypothesis. Only when I make a mistake, I update. In this theoretical algorithm, you can say, well, that's irrelevant because you will never have, you will always make progress. Why? Because theoretically, you touch all the hypotheses, you ask them what should be the prediction on this example. All of them say something. Worst case is that it's half and half, right? If it's half and half, you'll guess. And you will still eliminate half of them, right? So you will make mistake on each example, and therefore you make progress on each example. So it will take you just log size of C, but it's theoretical, right? So in practice, in a mistake-driven algorithm, you don't know when you will make the mistakes, right? So think about Perceptron that we just talked about. So it's possible that you start with a random weight vector, and for the next 100 examples, it's not making any mistake. You're happy.
And you can check that because you have the label. Right?
Yes. Every time I make a prediction, I get the label. So I have training data, right?
So you'll check with the label whether your prediction is right.
Yes, yes.
Okay. So when are you having office hours today?
5 to 6, yeah.
5 to 6.
Yeah. Okay, sure,
Thanks, sir.
sure. Hi.
Sure, like here,
Yeah.
we're talking about if we have, for example, y equals to 0, that means we're
No, y is not 0. Y in the previous slide, it's y is plus or minus 1. It's the label.
Oh, right. Oh, no, I see. Okay. All right. Thank
Okay?
you. Yeah.
Sure.
it fell 10 minutes back, okay. I'm like, it's falling, it's